Leaving groups, the leaving groups, which is given the symbol Lg, or just Lg, L dot. SN2 must have a good leaving group, or the reactions must have a good leaving group. In fact, SN1 is the same. You always need something such as, in this case, a halogen that leaves readily on its own. Good leaving groups are weak bases, meaning, again, they can stabilize their charges. The same factors that make a weak base, species a weak base, also makes it a good leaving group. So remember, a good leaving group is a stable base. It's not reactive. One way of looking at it is, of course, and we studied this in, remember, the chapter 2 on acids and bases, is if you look at the conjugate bases of strong acids in the top half of the pKa table with pK values of less than about 8. Okay, so it's not exactly at 8, it's somewhere around 8. So 7, 8, 9 is okay. But as you get up and up, let's say 12, 13, these are becoming now bad bases. These are becoming bad bases. Now, here are the good bases. You have iodine, which is equal to water as a good leaving group, because water, in this case, would have an oxygen with a positive charge on it if it has 3 bonds. So this would be the best. This would be the best leaving group because they are the weakest bases. And Cl would still be a good leaving group, but it's much better than, let's say, F. And I'm putting F here because we will not use, so this is a bad leaving group. And we won't actually study them. So in this case, iodine is a larger atom than bromine, then chlorine. Fluorine is the smallest, so it can stabilize the charge. Remember, accommodate the charge readily because it's bigger. Remember how the size, as you go down a group, the size increases, and that makes the conjugate base more stable. You will never, see these as leaving groups. These are very, very bad leaving groups. Very bad leaving groups. Hydroxide, alkoxide, and amide, carbanion, hydride. Again, their pKs are very high. So their pKs are about 15. So this is a pK. This is about 15. This is 35. This is around 50, and this is around 35. So they're very bad, but they do have exceptions. However, that may be visited in organic too. So again, you need these good leaving groups. You need water as a leaving group, not AOH as a leaving group, Br, and Cl. The nucleophile, the effect of the nucleophile, very important. We need a strong nucleophile for SN2, and there are trends to follow here. We need negative charges. If you have a negative charge, it means you have a stronger nucleophile. So if I have hydroxide here versus water, notice how I have a negative charge, the lone pair there. The rate of water attacking or the rate of the reaction of water as a nucleophile would compare to around 3 million for the hydroxide. So these two are good nucleophiles. Well, ammonia is a good nucleophile, but the amide is even better because it's what it's charged. So be able to remember that, again, negative charges on those species make them better nucleophiles. Nucleophilicity, that's the concept of where nucleophiles come from, decreases to the right in the periodic table, which actually correlates with basicity. So if you recall, this one, if we go to the left here, this means we have an increasing basicity. They're more basic. So these are very unstable bases, but they make up for good nucleophiles, which means, again, which correlates with increasing nucleophilicity. And of course, this one violates the opposite, which is basically we have an increasing electronegativity. And why is that? You actually need an unstable base if we are, again, talking about going horizontally, to be as a nucleophile. And the reason why is because if you have a more electronegative, so in this case, if you have a more electronegative atom, the electrons are held tightly. And if they're held more tightly, okay, they are less available for the reaction. So if they're held tightly, they're a more stable base, means that reaction is unwilling to take place. Now, when you go down a group, the nucleophilicity actually increases. So in this case, so we have an increasing nucleophilicity, but the opposite is increasing basicity. And the reason why, and we're just going to keep it simple, is that these right here are more polarizable. Once again, the electrons are not held tightly. Electrons are more loosely bound, which makes them, again, more available. So that would be, they would be available for the reaction. So nucleophilicity versus basicity, they're not the same concept, believe it or not. While it does parallel basicity, as we did see here in 2, it doesn't in 3. And just quickly is that because they have different definitions, just quickly, the difference between nucleophiles and bases is that nucleophiles in kinetics, they attack electrophiles. As you see here, the nucleophile is attacking another atom, carbon, replacing it. So this is based on the rate constant. Bases are actually thermodynamically defined, and they attack protons. Like in this case, this proton right here is lost to the water. And you use the equilibrium constant as a way of understanding the basicity. So pay attention just again to these three rules. They should help you discern what's a good nucleophile from a not so good nucleophile.